This presentation describes both the origin of the universe and explanations of its main features. The motivation for this theory comes from the problems in contemporary science, in particular the recent observations by the James Webb Telescope. This has shown that the widely accepted Big Bang theory has difficulty in explaining the formation of the earliest galaxies and also with the clumpiness of the universe. In addition, it has problems with the entropy of the universe and the excess of matter over antimatter. Physics has been unable to reconcile general relativity with quantum theory. Contemporary physics is based on the continuous space-time, but if everything is quantized, then it is possible, but not essential, that space-time is discrete, with the continuum just a macroscopic approximation, although a very useful one. In the following theory, it is assumed that the universe is discrete and that it is created from nothing. The fundamental particles are abstract rather than material. Material particles arise from the mathematical relations between the abstract entities, and the entire physical universe is an interpretation of the mathematical universe of the integers. The concept of nothing in this theory is more comprehensive than in most other theories. Obviously, there are no material particles here, but neither is there any pre-existing space, nor time, nor any vacuum state. There are no pre-existing physical laws, but the laws of arithmetic are required. The absence of any absolute information is crucial to this theory, as information is a restriction on generality. The most fundamental feature of a physical universe is that of time and space. A topological space consists of a set of objects and an ordering, such as proximity, between them. The basic objects are abstract entities whose only intrinsic property is an individual identity. The universe cannot contain a specific number of entities, as that would be absolute information. Instead, it must contain all possible such numbers, and these are ordered by the successive function of arithmetic, which defines a universal time. A space is created from subsets of three abstract entities, where the number 3 is chosen arbitrarily for the best chance of corresponding to the real world. Labeling each entry with a numerical identity allows a proximity order. The numerical identifiers of the basic entities also constitute absolute information, so they must be exchanged. This is a key feature of this theory that distinguishes it from other discrete theories of matter, and is the origin of quantum theory. The products of these exchanges generate the symmetric Aka permutation group on n entities, where n is the number of entities. Formal momenta can then be defined as the eigenvalues of a maximum length cycle of the group acting on individual entities, thereby introducing Newtonian material concepts into the theory. Quantum theory is thus the theory of the relativity of all matter. These formal momenta do not commute with the position coordinates defined by the identifiers, and this leads to a Heisenberg uncertainty principle. This can be described by a Fourier transform on the space of an n cycle. The symmetric group Sn on n objects has rank n minus 1. So only n minus 1 quantum numbers can be independently specified. This means that the uncertainty principle is actually much more widespread than simply the Heisenberg uncertainty relations I've just mentioned. The commutation rules for the symmetric group are usually described in terms of the n minus 1 exchanges of an identifier, which we call A, with the adjacent number a plus 1 for a in the range 1 to n minus 1. These exchanges do not commute with the formal momenta, so we'll change them, leading to the exchanges being associated with Newtonian forces as something which changes momentum. The discrete space can now be described in terms of the symmetric group and its subgroups. The group acts internally on a single subset point by means of a local S3 subgroup, and externally on the set of all points by a conjugate Sn-3 subgroup. The total space at time n is thus the coset space of Sn, symmetric group on n objects, modulo the product of the two groups S3 and S-3, with the exchanges acting as objects within the space. Contemporary physics is based on the idea of a continuous space. So in order to show how this theory relates to that concept, it is necessary to show how the discrete space can be made into a continuum. In fact, there is a very simple relationship between the discrete space and a very specific type of continuous space. The exchanges of an identifier A with A plus 1, as mentioned before, can be represented by a matrix with elements 0 and 1 acting on an n-dimensional vector space. These elements belong to the n-dimensional general linear group over the field of integers modulo 2. Replacing this two-element number field by the real number field R injects the discrete coset space of Sn modulo S3 times S minus 3 into the corresponding general linear coset space that defines the well-known Grassmann space. The Grassmann space is a set of all three-dimensional planes through the origin of the n-dimensional coordinate space, hence defining a form of multiverse associated with each of these three-dimensional planes. Special relativity applies to a multiverse component of three spatial dimensions supplemented by the evolutionary time with the zero-dimensional discrete space treated as being embedded in this component. The movement of a hypothetical observer in this four-dimensional space defines a world line along which a subjective real time may be defined. These subjective motions obey special relativity with the hypothetical observer seeing the universe as a projection into their rest frame. Early in the history of relativity theory, Minkowski showed that these projective geometry arguments lead to special relativity in a hyperbolic space of signature 1, 3, where 1 represents the time dimension, 3 the spatial dimensions. Obviously, this treatment leads to numerous anomalies that are the subject of a later slide. The discrete points and exchanges appear as particles in the conceptual continuum. A hypothetical observer has to use the exchanges to deduce the geometry from observations of the particles. As these are subject to the Heisenberg uncertainty principle, the universe will not appear to be locally flat. The way in which this arises can be described through the relationship between the characters of the symmetric groups n cycles and the general linear group. This was described by Schur more than 100 years ago in his theory of the polynomial representations of the general linear group. These characters lie in the diagonal elements of that group. The energy dual to the time translations is not related to the symmetric group, but would behave in a similar manner. In this, basically, the momenta or energy lie in the Lie algebra of the general linear group, and therefore define a form of deformation of space-time. This theory has considerable resemblances to the basic forms of loop quantum gravity. The theory treats time and space on slightly different footings, and it also describes the space in terms of loops. The spatial vectors associated with the n cycles of the symmetric group are automatically quantized as previously described, and they define quantized triads, whilst the energy associated with time semigroups are not automatically quantized, but will behave in a fairly similar way. The loops of the quantum space are generated by products of the exchanges, which are general forms of epicycles, essentially. These loops are not confined to a single three-dimensional space, so they do not provide a quantization of these spaces on their own, but only of the full Grassmannian manifold. The relationship between Hilbert spaces and Grassmannians in generalized quantum theories is well known, but this does not provide a quantization of space-time as it is usually known, i.e. a four-dimensional space-time. Relativity is only a crude macroscopic approximation in this theory, and there are many differences. First of all, the evolutionary time breaks the local Lorentz group symmetry, and as it increases, it provides energy and new particles, so driving the expansion of the universe. Thus, it may provide an explanation of dark energy, with the addition of an energy creation tensor being the simplest way of accommodating this in general relativity. The next anomaly is that a single coset point appears in 6 different locations simultaneously in the three-dimensional approximate continuum. This could account for there being 5 times as much baryonic dark matter as ordinary matter. A further factor is that the natural motions generated by the exchanges are epicycles at constant time and epispirals in general. Causality also differs as symmetry at equal evolutionary times provides a form of long-distance correlation that would not be expected on the normal causality of special relativity. So it provides an explanation for a form of quantum entanglement. In an abstract theory, the theory of forces is the theory of accelerated motion. In a geometric theory, this is the theory of second-order G structures, where G is a transformation group acting on the space, with cohomology describing functions on loops within the space. This applies to both the symmetric group and to the approximate symmetries associated with the conceptual continuum. With a single subset point, each entity has 2 internal degrees of freedom, describing the other subpoints of which it can also be considered to be a member. So this provides 6 extra internal dimensions for the point. And on this, the symmetric group of S3 also combines with these operations of the internal 6-dimensional space to generate an SU3 unitary gauge group, with the exchanges carrying the gauge fields like mesons do in physics, and particularly as in the strong interactions of the baryons. Relative to the external space, a point object has 0 length and defines a 2-component Cartan isotropic spinor. This requires the extension of the theory of the symmetric group by the number field 0, 1, as this has non-trivial cohomology. and this leads to the spinor representations of the symmetric group. Each physical sort of operational cycling operation of the symmetric group corresponds to both a vector and to a spinor representation, but there is no one-to-one correspondence between particles as defined by the spinor representation and the vector representation, as would be expected in supersymmetry. So this is definitely not equivalent to supersymmetry. It is simply part of the general theory of the symmetric group. In physics, particles are normally described by spin helicity and momentum. Within a curved space, the energy momenta is a much more appropriate and generally coordinate and variant measure of the particle's energy and momentum. These symmetric second-order tensors can be described in terms of their eigenvectors according to the Segre classification. So for massive particles, the highest symmetry applies to the type 1, 3 with one time dimension and 3 spatial eigenvectors. If all the spatial eigenvectors have similar eigenvalues, then there is a symmetry group of SO3 associated with these spatial transformations. And this might be the origin of the isospin group in physics. There are sort of three other sort of types, and it's possible, as will be mentioned later, this might be associated with the Higgs field. The maximum symmetry group of a coset point is then SU3 times SO3 from the energy momentum tensor and U1 from the phase of the spinor. The relativistic subjective time breaks the symmetry as it has to select one out of the three constituent basic entities as the one which provides the definition of the subjective time. This provides a model for a baryon where the energy momentum symmetry is interpreted as isospin. The exchanges carry gauge functions for each of these symmetries, hence act for both strong, weak, and electromagnetic interactions. In order to accommodate leptons in this theory, there would have to be free entities as isolated objects with no internal symmetry. These would then have isospin and electromagnetic type symmetry. Rest mass for such particles can only come from the evolutionary time translations, which generate an energy component. If this were to be compatible with the standard model of particle physics, then the Higgs boson would have to correspond to one of the exotic energy momentum types in the Segre classification. The most probable one of these is that it has a conjugate degenerate pair of eigenvectors plus two spatial eigenvectors. In this way, this could account possibly for the standard model of theoretical physics. Like the Big Bang model, this model starts from a finite origin, but progressively from a null origin rather than any explosive state. So I refer to it as the little whimper universe. And this resembles many sort of features of the macroscopic actual physical universe, such as babies, trees, etc., which all start small and grow. The James Webb Telescope has shown that galaxies start to form earlier than the big model predicts, and that the early universe is more clumpy than expected. The Big Bang theory also requires the very arbitrary feature of inflation to account for the homogeneity of the early universe, without providing any good explanation of why this should actually or how it should occur. And likewise, the Big Bang theory also fails to explain the increase of entropy in the early universe. This problem with entropy is also characteristic of many of the cyclic alternative bounce models. The excess of matter over antimatter is also a problem with the Big Bang theory. In the Little Whimper universe, galaxies grow earlier in the universe, in part due to the growth of the universe. So it's more a form of a tree-like growth rather than condensation. Homogeneity in the Little Whimper universe results from the symmetry. So there is no need to introduce the concept of inflation. Time asymmetry also causes the excess of matter over antimatter, since the distinction between matter and antimatter in this theory is with the direction of time. The Little Whimper universe exists relative to itself, with hypothetical conscious creatures holding the subjective information. Consciousness, from the point of view of mathematics, is an interpretation of a higher order language that can talk about itself by means of propositions about propositions. In the real world, consciousness is a flow of experience that defines a flow of time. In the Little Whimper universe, a flow of subjective time is related to a specific entity. These entities are immortal. A single such entity is associated with many points and hence particles. This creates the possibility that it could be associated with a conscious mortal material creature, although I've certainly not done anything to show that that is the case, but obviously in the real world such creatures do exist. The universe evolves by logical induction as regards the existing matter, but when new matter is created, its form is not determined because the subjective information is simply determined as the most probable situation. But there is a possibility that a hypothetical creature could, in fact, affect the outcome of the future material by simply effectively willing it to do what it wants to do. And so there is a possibility of a state of newly created matter creating a limited degree of free will. Conventional physics works backwards from observations, whereas the Little Whimper theory tries to work forwards from metaphysical arguments. This means that in order to explain cosmology, it also has to explain how all forms of matter are created, rather than simply assume the existence of the known particles and atoms such as hydrogen, photons, etc. At a superficial level, this theory seems to work reasonably well, suggesting both how the universe evolves at cosmological scale and how the material bodies might be associated with immortal souls.